thanks a lot for giving me the opportunity to share this work for this and closing this workshop. Thanks for the organizers. So I will be talking about clustering solar wind observations at 1IU with self-organizing maps. So this will be mostly the results that have been already published in my first paper. I'm a PhD student, almost going towards the third year of the present Yasmina Magdalenic. So we are talking about solar wind. Solar wind, as you may know, it's characterized by different kind of transients, which we usually call stream interaction regions, which are regions where the two streams coming from the sun, one slow and one fast, are interacting, and those are important, as Simon has already talked about, are important because they can cause geomagnetic storms, as well as interplanetary coronal mass ejections that are the second transients occurring in the solar wind, and it's related to something coming from the sun. It's basically a plasma blob which is ejected from the sun, and it's propagated through interplanetary space. And we have clear signatures at 1IU as well, because it's a magnetically coherent structures that is interacting with the magnetosphere and causing also geometric storms. However, these are bigger scales phenomena. There are also smaller scales phenomena occurring in the solar wind, such as the magnetic reconnection, or one picture of what we call reconnection exhaust. You can see it in the right pictures in this slide. So this work is focusing on clustering the observations, and then thanks to a catalog of Ericsson et al. 2022, we contextualize the reconnection occurring in the types of wind that we find with our clustering. So this is the pipeline. In this specific work, we are focusing on a 3-second cadence data of wind spacecraft. So we're talking about around 5 million data. And we are focusing on 4 features: velocity, proton velocity, magnetic field strength, proton density, and the logarithm of the proton temperature. Yes. So the pipeline is, as you can see in the screen. Minimize that. Yes. So you have the input time series. Then what we do is per processing. So we remove the bad quality data. We robust scale the data. What is robust scaler? Is a different type of scaler, which is not the usual type of scaler. Is the standard, which it removes the mean and scales to the variance. In this case, the robust scaling removes the median and scales the data according to the interquartile range. Why? Because since we have transients are more or less outliers in your dataset, you don't want that these kind of features are affecting your mean and standard deviation, and so you don't want it to be like affecting your data, let's say. So what we do then, we train a self-organizing map, of which we talk about very soon. We visualize the results, we cluster the map we obtain, and then we look at the cluster time series. Clustering will be done with simple k-means, and the number of clusters will be found with the needle method combined with Kalinski-Arbrats and silhouette scores. These I will not talk about. If you are interested in, just send me an email, or we'll talk about it in the question section. So, okay. Self-organizing map. What are self-organizing maps? Is a one-layer network, 2D map, x times y. Each neuron is representative of we can say an average solar wind state y. So what do? Is we have our input data, which is a 4-dimensional data point. We present it to the network, and then the network, which is a matrix of weights, you find the best matching unit, which is basically the neuron which is closer to the input data. Then what you do, you find a neighborhood defined by a Gaussian function, as you can see on the right. And then what you do, once you identify this neighborhood, you shift these weights towards the input data. Why? Because in the end, once you finish the training of the map, your map tries to be a local average of your input data set. Of course, you don't want the map to be too close to your input data, but you also want the map that is also topographically reflecting the input dataset. So in our work, we use a GPU implementation of the self-organizing map with this set of parameters. Let's not talk about it. I mean, if you are interested, we talk about it later. So the metrics that we used is the quantization error, which is a measure of how well your data is represented in the map, and a topographic error, which tells you how your map is topographically correct with respect to the data. What is so the quantization error? It's more or less more intuitive. The topographic error is less intuitive in the sense that what is an error? An error is when you have your best matching unit, which is the neuron which is closer to your input data, and then the second best matching unit has to be in the neighborhood of that neuron. If it's not, then that's an error. Okay, so this is the plot of the quantization error and topographic error according to the iteration of the map, and as you can see, we choose maximum number of epochs 9, and what you can see here, 9 is corresponding to the value of the minimum topographic error. So we visualize the results of the SOM. So the SOM is a matrix of a 2D matrix. Okay, each weight has the same input data dimension. We can see how the physical features are distributed on the map, as you can see on the right, and we can see how the neurons are distributed on the map. As you can see, I mean, the red neurons are the neurons that have been associated to a reconnection event, let's say. And as you can see, they are clustered locally, which is a good sign, but they are spread out all over the map. Why? Why? Because the reconnection is happening in different solar wind states. What are those states according to k-means? So we cluster with k-means. We have 5 clusters as optimal number of clusters. And as you can see, there are more events, reconnection events in the pink cluster, which is also the cluster with low solar wind speed, higher density if we compare it with the brown cluster, and low temperature. And so on. You can also see that in the brown cluster, which is characterized by higher velocity, you see less events, and you see more events in the blue clusters. Ora, now we can interpret the clustering results by going back to the original time series. How do you do that? You find the best matching units and you just cluster back the time series. And what we identify is that if you look at this time series, it's my favorite month, July. You have all the events that you need. You have 3 stream interaction region from 9th of July to 21st of July, I would say. You have 4 ICMEs from the 22nd of July until the end of the month, and you have also a fast streams and slow solar wind. So we identify the pink cluster as the slow solar wind, the brown cluster as the highly galvanic wind. I will not talk about this, but highly galvanic wind, I call it like that because it's a cluster which is characterized by high alphanicity. If you want to talk about alphanicity, just ask later. Then there is the compressed slow wind, which is the blue cluster. Also, meanwhile, I'm talking, just look also the feature distribution on the left. Then we have the compressed fast wind, and then the ejecta. So compressed slow wind is that type of wind that comes. So what happens when you have an SIR? An SIR is a stream interaction region. So you have the slow stream that comes, then there is the fast stream incoming. So what you have first is the compression of the slow wind. Then what you see later is the compression of the fast wind, and then afterwards you can see the fast high-speed stream. And that's what actually you see in this in this cluster time series. The ejecta is basically the magnetically defined structures like ICMEs. So there are other types of solar wind classification like the Chuborowski ones that are trying to classify the solar wind according to the origins, and it's a four-type parameter scheme. You can see it on the left, and we compared our cluster content within the Chuborowski classes, and as you can see, we have that the coronal origin class of the of Zuborowski is mostly present in our island Venic wind. The streamer belt class of Zuborowski is mostly present in the slow solar wind, and the compressed slow wind is mostly associated with the sector reversal wind. And 93% of the ejecta is present of our ejecta is present in the ejecta cluster of Zuborowski. But what is interesting here is the compressed fast wind, because compressed fast wind is it's comprised by streamer belt wind, ejecta, and compressed fast wind. Why? If we look at this, and again, my favorite month, you can see that at the bottom, you can see that for Zuborowski, the compressed fast wind in this specific case is an ejecta. And that's, I mean, sort of an error because that's not an ejecta, it's just a part of an SIR. And this also explains why in their paper they said that they had a bimodal distributions of the ejecta, because they had like this magnetic cloud-like ejecta, which are mostly ICMEs, and then they have this mixed streamer belt and coronal wind ejecta class that, I mean, at least from the results of this paper, can be explained by this compressed fast wind. Then, of course, we contextualize the reconnection. We count the reconnection within the cluster, and we see that most of the reconnection is happening in the slow solar wind cluster, followed by the highly Venic wind, and then we have the rest of the reconnection between the compressed slow wind and the compressed fast wind, and a small portion of in the ejecta. It is mostly compatible with Zuborowski's classification scheme. Of course, with the ejecta there is a small I mean, there is a difference because part of the ejecta in Zuborowski is our compressed fast wind. So, concluding with this last slide, how can we put this on board? Yeah, I would say yes. The only thing is that you have to try to do an optimization on the size of the map, because computing the best matching unit can be computationally expensive if the map is too big. This is an example that I had is also in this paper, where I compared the results of a map, of the full map, compared with 70% of neurons map. Basically, it's like a full map and less neuron map. And as you can see, the results are not changing that much. So there is a field here where you can just do an optimization over the number of neurons, and then find the most optimal map to be maybe uploaded on board. So you try to minimize the number of neurons, and you find a trade-off between performances and accuracy, let's say. So to conclude, we have found 5 clusters. Those clusters are compatible with previously and mostly and widely used schemes for classifying the wind, and this compressed fast wind can explain this bimodal distribution of ejecta that has been seen in this widely used scheme. Compressed slow wind and compressed fast wind are typical in SIR and ICME sheet, and as I said, reconnection events are associated with slow solar wind, followed by highly Venic wind, compressed slow wind, compressed fast wind, and ejecta. So, and our board implementation can be feasible with a study on optimizing the map size. On the right, you can see you can have the QR code of this paper if you want to know more about it. And I conclude thanking you.
Questions? people are a bit tired after like the whole day of talk.
Can you hear me?
Yes, can you hear us?
Okay.
Yeah. Yeah. So yeah, okay. Then I'll ask a question about the this reduction of data. So you went, sorry, not data, the neurons, yes. So you went for 70%. Probably you could have gone for.
Sorry, I don't hear you very well.
You cannot hear me? Yeah, yeah. Okay. Can you hear me now? Hello?
I cannot hear you very well.
Strange.
Can you maybe send the question in the chat?
Yeah, yeah, let's send a question in the chat. Yeah, I have a good connection, then maybe you can type it. So just a question about, you know, if you like that choice for 70%. So can you hear us, Francesco?
Yes, now yes.
Okay, so George is asking to elaborate a bit your decision of choosing 70% of neurons and not perhaps going even lighter to see, I don't know, what's your intuition if you go lighter, less 50%, let's say, of neurons? You expect much difference?
Well, as I said, in the end, self-organizing map is a data reduction technique. It's not reducing the feature space, but it's reducing your input data, basically. It's like creating averages, average states of the solar wind. Basically, each neuron is basically an average state, so a state of the solar wind. Well, choosing lesser and lesser neurons will correspond to more averaging. So what can happen is that you either may lose a cluster because you're averaging too much if you use lesser and lesser neurons, and that depends on your needs and what clusters are merging, because if I say if the compressed slow wind and compressed fast wind are merging together, it's not a big deal. It becomes just compressed solar wind. But for instance, if the slow solar wind becomes it's merged with the fast or highly advanced wind, then that becomes a problem. So what I would do here, if you one is planning to implement this kind of thing on board, either you do a grid search where you have 10% of neurons, 20%, 30%, 50, 40, 60, and so on, or you just use Optuna to optimize on the number of neurons. But I would rather do a grid search in this case, because I think like a grid search with 10%, 30%, 50%, and 70% of neurons may be a good way to go.
Yeah, and one aspect is the SOMs. The other aspect is how easy it is to have k-means implemented there, right? Because you also need k-means.
No, you don't need k-means because k-means is done at Earth. So once you what you would upload on the spacecraft is the clustered already. So
but again, you have to calculate the difference. You upload the centers, and again you have to. So you're doing inference. You don't train it, but still, I think we have, because we had this discussion before. Has to run the SOM in the inference mode. So, but
no. Basically, what you have once you have trained the map and you clustered it, you have the cluster for each neuron, right? So on the spacecraft, you can upload the weights of the map plus the label of the cluster.
Okay.
Right? Yeah. So once you have the best matching unit, you are already clustering, because each neuron is already labeled with the cluster.
Okay.
number.
Yes.
So if you know that cluster, if you have a new data, you measure the best matching unit, meaning the neuron which is closer to your input data. You measure it. You know to which cluster it belongs. So you have clustered the data point, right?
Yes. Yes, I agree.
So if you want to implement it on board, you can just upload the weights plus the labels, and it's done. But the problem is that if you have a too large map, that can be computationally expensive, and then of course you have to optimize on the map side. Yes.
Yeah. That could be an open question, I don't know, for us for the coming months from Pedro and for Gianluca, because we saw that in the analysis of state of the art, there was a work of SOMs. So there is an opening there.
Yeah. It's in principle it's possible. The whole question is, it's all about time. If they have time to test, because already,
exactly.
Requesting them extra algorithms and more.
Yeah, because there is an advantage of using SOM over k-means, for instance, and the advantage is that with k-means you have only, you have centroids, and centroids are just one neuron, let's say. In this case, the clusters are represented by more neurons, so you have more adaptation on new data eventually.
That's something important to take in mind if you are looking about the onboard things, because you are looking at the zero level data. And if you remember, Francesco, the clustering was messed up when you have these outliers, which are very high intensity things.
Yeah.
So,
yes, that's why what you can do, you can flag the neurons which are around the neighborhood, the neighborhood of the how do you say, in the neighborhood of the cluster's boundaries on the map. If a data falls there, then you flag it and you say, well, this is classified like that, but be careful. Well, to be honest, you can even do, you can also see if this, I didn't talk about it, but this U matrix is a way of representing the data and the neurons which are further from each other.
Yeah.
One could also try to see if bad quality data are falling into region of the map where the neurons tends to be much more distant from each other. That could be also potential. So anomaly detection with self-organizing map is possible. So
I think level 0 data from in situ is much more noisy.
It's very
SDO.
very
so
noisy.
It's much more optimistic to try to address this.
There, I would even go for some filtering before using the AI on it. So because it will be very problematic.
Yeah.
What you have in the Omni data, that's very beautiful comparing to what you have in the real-time stuff. So.
But here in this work, I was using the 3 seconds cadence on board. So it's point. I mean, and also I think since it's a pointwise clustering. Even if your data are noisy, there is a high chance that a bigger amount of your data can fall in these boundaries between the clusters, or even in these regions where the neurons are far from each other. That's the issue that I see there. But if you flag those regions, then you may have a possibility to know already which kind of data can be bad quality.
The problem is that if you look at, for example, in Discover real-time data, and you look how bad the data looks like, they are like they will kill your compression region and your compressed wind and all the rest. So you will see no characteristics out of it because you will have too much of this jumps up and down.
That's true. That's true when you train it, but once you have trained it, I think, I mean, as I said, worst case, they are misclassified.
Yeah.
And I mean, you can live with that. but if you think about it, so if you flag the potential misclassified region, which I would say is the cluster boundaries, around the cluster boundaries, then you have a safety check already.
They actually do flag the data which could be the possibly bad, and usually they flag it well, which means that they must have some software already going through it. So one would have to really take a look at that.
Yeah.
And do some small testing.
Yeah, anomaly detection techniques, I would say.
I could imagine there's some problems when you work with MMS data or cluster data.
Yeah.
Yeah.
Depends on the data. If it can be clean.
Depends on the day. Yeah, I mean, of
Then
course.
it's also about the mission. That's what is complicated.
Oh yeah. If you go from ACE to Discover, that's like oof.
Yeah.
Yeah,
But the course of time, like, especially ion detectors, they are less and less efficient, more noisy, and so it's not the same data from the beginning to the end of the mission.
Yeah. And also, if you look, because you use magnetic field data and you use the plasma data, these are always different instruments, so they will be differently affected.
Yeah.
One will be noisy, and another one will not be, and then next time it will be vice versa. So
it's even more complicated for the ion instrument. Each sector of the instrument evolves differently.
Yeah.
And yeah, also I wanted to say that for classifying the magnetospheric region, very, very similar work has been done with self-organizing maps and by James Edmond I think it's in the US, and they compared with Brouillard results, and they are pretty much similar. So one could consider to benchmark whether it's easier to implement the SOM on board or the Brouillard.
The kind of classification I presented, not so difficult, because you have like big differences between regions, and
yes,
you can also decrease the number of regions. So I mean, at the first step, it can be pretty easy. Can be done with not all data. So, but then it depends on the accuracy you want, and like when we use transition regions to put things that are more complicated, or if you use a tags which is complex, you put things which are more complicated. If it's 1% of the data, it can be okay. If it's 50% of the time, then it doesn't make sense. So
yeah, exactly.
But I think if you can tune it and make it not too complicated. But
yeah.
Have a good trip.
Sorry, I didn't know.
Yes,
No worries.
no problem.
Have a nice.
Take care. Bye-bye.
Yeah. Yeah.